All right, our final video dealing with the gas laws deals with when you have a mixture of different gases together. So today we're going to talk about mixtures of gases. We're also going to talk about what are called partial pressures of gases as well. And so up until now we've only considered the behavior of one gas. We've considered oxygen by itself. But a lot of times gases are made up of a combination of different gases such as air. Air, for example, contains about 78% of nitrogen, about 21% of O2 oxygen, and then the other 1% is made up of like carbon dioxide, maybe some hydrogen, certainly some water. There's lots of other gases in air. So when we talk about the behavior of gases, a lot of times we have to consider a mixture of a whole bunch of different gases. So there was a gentleman by the name of John Dalton who observed that the total pressure of a mixture, a lot of times we write that as P and then a little t, capital T, down in the corner. So the total pressure of a mixture of gases equals the sum of the pressures. Remember, sum means addition of the pressures that each would exert if it was present by its own. So for example, in air, if we wanted to know the total air pressure, we could take the pressure due to the nitrogen plus the pressure of the oxygen plus the pressure of the carbon dioxide and so forth. And what we call each of these pressures, because they're a part of the total pressure, is we call them partial pressures. Because this pressure here of nitrogen is one part of the total pressure. So you can add up all of the partial pressures to get the total pressure. So if you're asked to find the partial pressure of a gas, basically all that means is you're considering a mixture of gases, and if I say what's the partial pressure of oxygen, it just means that you're finding the pressure just due to the oxygen component of that gas. So we can see here that the total pressure is equal to the pressure of one gas plus another gas, and depending on how many gases there are, you can just continue to add them together. Okay, and we can also do that with moles. Obviously, if you want to know the total number of moles, you can add up the moles of each of the substances amount, and you can get the total number of moles. So therefore, we can say that if we want just the pressure due to one of the gases, we use just the moles of that gas. If I want the pressure of, let's say, hydrogen gas, that's going to equal the moles of hydrogen gas times R times the temperature of the gases divided by the volume of the gases. But this part right here is what's going to give us just the pressure of our hydrogen. And then if you want another gas, obviously you do it the same way. You have to use the moles of just that gas. So therefore, if we want the total pressure, one way we can do that is we can get our total moles, and that'll give us our total pressure. Or you can take, like we looked here before, you can figure out the pressure of each individual gas and add them together, and there you can get your total pressure. So let's look at a problem with that. It says a gas mixture made from 6 grams of oxygen and 9 grams of methane is placed in a 15-liter container at 0 degrees Celsius. What is the partial pressure of each gas? So basically what that's meaning is basically what is the pressure due to the oxygen and what is the pressure due to the methane. And then they want to know what is the total pressure in the container. So first of all, again, there's multiple ways we could do this, but in terms of figuring out the pressure of the oxygen, just like what we talked about before, the pressure of the oxygen is going to be the moles of oxygen times R times T over V. So the first thing we need to figure out is how many moles of oxygen do we have. So if we start with our 6 grams of oxygen, we can say there's 32 grams in 1 mole of O2. Again, that 32 comes from the periodic table. And then we're just going to take 6 and divide by 32, and I get 0.1875 moles of O2. And that is what's going to go right up there. And just because we've done this a bunch of times, I'm not going to write the whole thing out. But now I'm going to take my moles. I'm going to multiply by 0.0821, my R value. I'm going to multiply by the temperature in Kelvin, and it was 0, so that's 273 Kelvin. And now I'm going to divide by the volume, which again, 15 liters. So 0.1875 times 0.0821 times 273 divided by 15. And that gives me a total pressure equal to 0.280 atmosphere. Now, when we look at the pressure of the second gas, obviously we're not going to do oxygen. This pressure here is just the pressure due to oxygen. So now when we come back to our other gas, our methane gas, basically we're going to do a very similar thing, but obviously instead of using the numbers from oxygen, we're going to use the numbers from methane. So first thing we're going to do is very similar to this. We're going to take our grams of methane, 9 grams of methane, 9.00 grams of CH4. We're going to convert that to moles. The molar mass of methane is 16 grams in 1 mole. So I'm going to take 9 divided by 16. That equals 0.5625 moles. And then again, just like our previous problem, we're going to take our moles of, in this case, methane, and we're going to put it into our equation. So the pressure of methane is going to equal the moles of methane, 0.5625 times R times the temperature was 273, I believe. Yep. And the volume was 15. So 273, a volume of 15, 0.5625 times 0.0821 times 273 divided by 15 is equal to 0.840. And again, this is pressure, so that is atmospheres. So now our final question here was, now that we found the partial pressure of each gas, so we know the pressure of oxygen, we know the pressure of methane, so we've gotten those partial pressures. Now they want to know what's the total pressure in the container. We take our pressure of oxygen, 0.280, and this is our pressure of CH4. So we go 0.280 plus 0.840, and I believe that comes out to be 1.12. Does that sound right? I think that's right. 0.280 plus 0.840 equals, yet 1.12. So we could say our PT, our total pressure, is equal to 1.12 atmospheres. And that's our final step, is adding those pressures together. All right, let's look at another example. What is the total pressure exerted by a mixture of 2 grams of hydrogen gas and 8 grams of nitrogen gas at 273 Kelvin in a 10-liter container? So I want to do this one a little bit differently. We could do it just like what we did, how we did the other one. We could get moles of hydrogen using our grams of hydrogen, and then we could get the pressure of the hydrogen. And then we could get the pressure of the nitrogen gas doing the same thing, and then we could have our 2 pressures, and then we could add them together. Remember that another way that we can do it, though, is we can get the total pressure by taking the total number of moles times R times T over V. And so if we just convert our grams of hydrogen, so 2 grams of H2, and then the molar mass is 2 grams per mole, so that equals 1 mole of hydrogen. And then let's do the same thing for nitrogen, 8.0 grams of N2. N2 has a mass of 28 grams per mole. 8 divided by 28 is 0.286 moles of N2. So now what we can do to get our total pressure is we can just add our moles together. So obviously 1 mole plus 0.286 is just 1.286. So to get our total pressure, we're just going to go 1.286 moles. That's our N times R times T over the volume, 10 liters. So I'm going to go 1.286 times 0.0821 times 273 divided by 10 gives me a total pressure equal to 2.88 atmospheres. Now, if you decide to do this differently, if you decide to get the pressure of the hydrogen and the pressure of the nitrogen, and then you add them together, you will come up with the exact same answer of 2.88 atmospheres. All right, and then our final thing that we're going to talk about deals with mole fractions. Now, the symbol that we use for mole fractions is a capital letter X. And what we use mole fractions for is we use them to express the ratio of the number of moles of one part of the gas over the total number of moles. So the moles of one gas over the total number of moles. Now, when we do this, we don't leave it as a fraction. So say we get an answer of 5/8. Even though we call it a mole fraction, we don't leave it as a fraction. You would actually take 5 divided by 8 and you would get 0.625. Now, what's nice about mole fractions is there are also no units. Don't put percent, don't put moles, there's nothing. You don't put anything for a unit in a mole fraction. It's just that decimal that is formed from that fraction. So when you do mole fractions, you take, like I said, the moles of one gas over the total number of moles. Make sure you include, when you do the total, the moles of that gas that you put on top as well. Okay, and then what you can do is you can actually use mole fraction. So here's our mole fraction right here, and multiply it by the total pressure to get the pressure of that gas. So for example, if this right here is the mole fraction of, let's say, nitrogen, and we wanted the partial pressure of nitrogen in a mixture, we could take the moles of nitrogen, divide it by the total number of moles, and then multiply by the total pressure, and that would give us our pressure of just the nitrogen. All right, so let's look at an example of this. It says a mixture of gases contains 12.47 grams of nitrogen, 1.98 grams of hydrogen, and 8.15 grams of ammonia. The total pressure is 2.35. What is the partial pressure of each component? So I'm not going to do the whole thing, but let's just say we want the pressure, let's just use that previous example of nitrogen. Then I would need the moles of nitrogen over the total number of moles, and then I'm going to multiply that by the total pressure. The total pressure is our 2.35, so that's going to go here. So really what we need to figure out is our moles of nitrogen. So I'm going to pause the video at this point. You should do the same. And let's calculate our number of moles of nitrogen. And let's calculate our total number of moles. I'm going to pause the video now. All right, so now that we're back, we've got our moles of nitrogen on top. I got 0.445. And then down below, I have my moles of nitrogen again, 0.445. My moles of hydrogen is 0.99. And my moles of ammonia as 0.479. And then when I take this number, the number on the top, our 0.445, and I add all of these up, and I divide them, I get a mole fraction of, and it looks like 3 significant figures, 0.232. And that's how I leave it. That's all I do, is I write that decimal down, no units, no nothing. Now, that is the mole fraction of nitrogen. So now what we can do is we just take our 0.232, which is, again, this value. We times it by 2.35 ATMs. And what that will give us is it will give us the pressure just due to the nitrogen. So we'll take 0.232 times 2.35, and that gives me a pressure of nitrogen equal to 0.545 atmospheres. So again, what that means is that of that 2.35 atmospheres of pressure, 0.545 of them is the nitrogen component. Now, we could do the same thing. It says they want us to know the partial pressure of each component. We could do it again for hydrogen and again for ammonia. And if we did, all three of them would again add up to that 2.35 atmospheres. And you do it the exact same way. So this is just an introduction to partial pressures, learning to use mole fractions, and hopefully this will help you in solving some problems dealing with this.